Hey there peeps, impulse. We're looking at elastic and inelastic collisions in 1D. That's the variety we're looking at right here with a large stationary object. Elastic. We know that in an elastic collision, kinetic energy is conserved and the action is like a bounce, okay? It goes boing. The two objects bounce right off each other and in that action, kinetic energy is conserved. So here's the before. We've got mass 1 smacking into a very, 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 very large M block over here. Okay? So you can imagine this to be like the immovable object. It's so massive that it really won't budge, okay? So we've got M1 coming in at velocity negative v1 naught. So it's the negative direction. We'll consider left to be negative. After it ricochets and bounces off of object M, it has velocity v1 naught positive, okay? So it's just boing, this happens in this collision and there's a ricochet afterwards. And so we're going to look at the impulse of that event. On the other side, we have the inelastic collision, where kinetic energy is not conserved. The action is a splat. It's like where the masses stick together, so M1 will come in at big M, this virtually immovable object, and go splat right here. So we have v1 naught in the negative direction. M1 comes towards the object in the before, and then the during is splat afterwards. The big object and the little object stick together, but there's no velocity. It just kind of smooshes up against the wall, and there's just no motion over here like that. That's the inelastic case. So let's look at what happens with impulse in the next pane. Thank you all. Alright, so let's take a look at the nitty-gritty of this impulse momentum stuff. Here we go on the elastic side. Over there on the inelastic side, we'll start with elastic. Okay, so J, remember that J is the symbol that represents impulse. Alright, all these quantities are vectors, vector, 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 vector. So we've got arrows on top of each. So we have J sub E, meaning impulse of the elastic collision is delta P, or the change in momentum, which is P final minus P initial. Momentum final minus momentum initial, or original. So we've got impulse for the elastic collision equals M1 v1 naught. Remember that the bounce had the same speed, so we called it v1 naught, but it was in the positive direction when it bounced. Okay, so that's why this is positive over here. Minus m1, and of course the original velocity came in at the negative, with the negative direction, so here's the negative sign over here. So we got m1 v1 naught plus, well, it becomes plus over here. That's the deal. We have negative and negative, so this is all positive over here. So we've got the impulse on the elastic side equaling 2 m1 v1 naught. Remember, big M has v final equals to 0. It's so huge it didn't even budge, okay? It's kind of that immovable force. So we're going to imagine that it's so huge. Or in the case where it's a wall, the wall is fixed to some kind of foundation perhaps. A wall, though, would violate in this case the conservation momentum, because conservation momentum really means that you have no external forces. So that's why I just consider this big M to be so huge that it's the same thing as almost an immovable object. Very, very close to it. Alright, let's look at the inelastic side. So we've got J sub I for inelastic equals delta P again. Momentum final minus momentum original. Okay, in this case, the final velocity was 0. This is the splat over here, right? Okay, and all we have is the incoming momentum, which is minus m1 times negative v1 naught. So this is just m v1 naught. Okay, so that's what it is. The impulse here for the inelastic collision is m1 v1 naught. Notice that it's actually 1/2 of this. This is double that. And so the elastic collision is actually much more dangerous, has twice the impulse as the inelastic collision. So what does it mean? Well, we've got some very big things here. So, watch it. Interpretation is that the elastic collision will deliver twice the impulse as the inelastic collision and are therefore more damaging. This is a huge reason why cars need crumple zones. Crumple zones try to do this. They try to have things kind of stick together. So, you know, if you're in that unfortunate situation where your car has smashed into a wall or a tree, you don't want to bounce off of it. That would be much worse. So the old cars with no crumple zones used to do that. The old things, there were rigid shells, and And they would bounce off of objects and cause much more damage to the occupants because of this, because it's twice the impulse, okay? That's what crumple zones do. All right, that ends this. Thank you very much. More ad, out.